Hello everyone, welcome to my channel Chemical Engineering Knowledge. In the previous lecture we have discussed about the interface mass transfer. In this lecture we will discuss about the phase equilibrium. The phase equilibrium. We will discuss about the phase equilibrium. The phase equilibrium. The phase equilibrium is very important phenomena in the mass transfer. The mass transfer and in thermodynamic. Thermodynamic. Usually in the thermodynamic we are studying phases in equilibrium. So the phases can be the solid phase, it can be the liquid phase, and it can be the gaseous phase. The solid phase can be activated carbon, it can be catalyst. The liquid phase can be water, it can be ethanol, kerosene. The gas phase can be air, it can be sulfur dioxide, it can be flue gases, it can be carbon dioxide. So the phases can be solid, liquid and gaseous. And these phase equilibrium are very important in the various mass transfer process, like in the gas absorption process and in the distillation process and the stripping process. These phase equilibrium are very important in the adsorption process. It is very important in the distillation. It is very important in the stripping process. It can be important in the liquid extraction, in the solid liquid extraction. So these phase equilibrium are very important in the mass transfer and in thermodynamics. Usually in thermodynamics we are studying the phases of in the equilibrium. We are using equilibrium study are very important in the thermodynamics. So in the thermodynamics we will discuss the various phases of. Now in this lecture we will discuss, our main focus is on the phase equilibrium. For example, suppose we have a vessel. Suppose we have a vessel. This is a vessel. Suppose we have a vessel. Take a vessel. Fill some water. This is the water. Fill the vessel with some water. This is the water, the liquid water. Now pass some air through the vessel. Also pass some sulfur dioxide through the vessel. We take a vessel, we fill it with water up to some height, then we pass air through the vessel. After passing air, we close the valve. Suppose this is the valve. Close the valve, and then we pass the sulfur dioxide through the vessel and close the valve again. After a certain time, the sulfur dioxide was absorbed in water, liquid water. But some of the sulfur dioxide was also dissolved from liquid water to the air again. So at the start, the sulfur dioxide was absorbing in the sulfur dioxide was absorbed. At the start, the sulfur dioxide was absorbed in the liquid water. At the start, the sulfur dioxide was absorbed in the liquid water. Then some of the sulfur dioxide was released from liquid water to the air again. So this was the vessel. This is the air. This is the sulfur dioxide. This is the liquid water. This is the liquid water. The sulfur dioxide. The sulfur dioxide is absorbing. Sulfur dioxide is absorbing. At the start, the sulfur dioxide was absorbed in the liquid, but after a certain time, some of the sulfur dioxide was dissolved from the liquid water. Now, a time reached in the rate of absorption. The rate of absorption is equal to rate of desorption. Then a time reached at which the rate of absorption becomes equal to the rate of desorption. Then at that time we said that this system is in the phase equilibrium or in the dynamic equilibrium. Dynamic equilibrium or phase equilibrium. First of all, we take a vessel, we put some water into it, we pass air and sulfur dioxide. Sulfur dioxide was absorbed, but some of the sulfur dioxide was also dissolving. After a certain time, the rate of absorption becomes equal to the rate of desorption. At that time, we said that this system is in the phase equilibrium. We said that the liquid water and the sulfur dioxide is in the phase equilibrium. Now, what happened during this process? What happened during this process? This was a vessel. This was the vessel. This was the vessel. Water. This is water. This is air. This is the sulfur dioxide. When we entered the sulfur dioxide into the vessel, the sulfur dioxide was absorbed in the water. But some of sulfur dioxide was also dissolved. After a certain time, equilibrium was reached, at which the rate of absorption was equal to the rate of desorption. At that time, we said that the water and sulfur dioxide in the equilibrium. Now, how can we relate the relationship between the concentration of sulfur dioxide in the air and the concentration of sulfur dioxide in the liquid water? The concentration of sulfur dioxide in the air is denoted by YA. And this concentration of sulfur dioxide in the liquid is denoted by XA. At the start, when we enter water into the vessel and we fill the vessel up to some height and we enter the sulfur dioxide into the system, then the sulfur dioxide was absorbing in the system, and after a certain time equilibrium was reached. Suppose we enter sulfur dioxide into the system, the concentration of sulfur dioxide, the concentration of sulfur dioxide in the gas was very high. After a certain time, the sulfur dioxide was absorbing in the liquid water and its concentration was decreased. At equilibrium, concentration of sulfur dioxide was reached to YAE. At equilibrium, the concentration of sulfur dioxide. Sulfur dioxide, suppose it is component A, air is component B, and water is component C. So the concentration of sulfur dioxide is denoted by YA, and the equilibrium concentration of sulfur dioxide in the air is YAE. Similarly, the equilibrium concentration of sulfur dioxide in the water is XAE. So when we, at first time, when we enter sulfur dioxide, it was absorbed into the water. At equilibrium, the concentration of sulfur dioxide in the air was XAYAE, and in the liquid, the concentration of sulfur dioxide was XAE. Now, how the concentration of sulfur dioxide in the air and the concentration of sulfur dioxide in the water can be related? So, first of all, we pass sulfur dioxide. When equilibrium was reached, concentration of sulfur dioxide in the air was reached to YAE, and in the liquid it was reached to the XAE. Now we increase the pressure, or we increase the concentration of sulfur dioxide in the above place. We increase. When we increase, suppose at first experiment, the equilibrium concentration of sulfur dioxide in the air was YAE during experiment 1, and in the liquid it was XAE1. Then we increase the concentration of sulfur dioxide in this place. Again we enter more sulfur dioxide into the system, and the sulfur dioxide was absorbed in the water. Sulfur dioxide was absorbed into the water. Some was removed from the water. But when we reach to the equilibrium, the concentration of sulfur dioxide was, when we determine the concentration of sulfur dioxide at the air or in the above place, at the second experiment, it was obtained to be YAE2. In the liquid phase, the concentration of sulfur dioxide was reached to be XAE2. XAE2. Similarly, when we further increase the concentration of sulfur dioxide in the air, in the above space, equilibrium was reached, some sulfur dioxide was absorbed, some was removed. After equilibrium, the concentration of sulfur dioxide in this above place was reached to YAE3. In the liquid phase, the concentration of sulfur dioxide was reached to XAE3. During the fourth experiment, the concentration of sulfur dioxide in the above space was reached to YAE4. In the liquid, it was reached to the XAE4. Similarly, when we further increase the concentration of sulfur dioxide in the above space, sulfur dioxide was absorbed, but some was released to the air. At equilibrium, the concentration of sulfur dioxide in the above air was reached to YAE5, and in the liquid, the concentration of sulfur dioxide was reached to XAE5. Concentration of sulfur dioxide at equilibrium during experiment number 5. Similarly, after a certain time, when we further increase concentration sulfur dioxide, it was reached to YAE6, and liquid it was reached to XAE6. During the 7th experiment was further increased to YAE7, XAE7. So how can we obtain a relation between the concentration of sulfur dioxide in the air and the concentration of sulfur dioxide in the liquid water? During experiment number 1, suppose this is experiment number, and this is the concentration of sulfur dioxide during the equilibrium in the gas phase. in the concentration of sulfur dioxide in the liquid phase. This is the equilibrium concentration of sulfur dioxide in the air. This is the equilibrium concentration of sulfur dioxide in the water. And this is the experiment number 1. Experiment number 1, concentration was XAE1, YAE1, that was XAE1. During experiment number 2, that was XAE2, XAE2. During experiment number 3, concentration in the gas phase was YAE3. In the liquid phase, the concentration of sulfur dioxide was XAE3. During experiment number 4, the concentration of sulfur dioxide in the air was YAE4. In the liquid, it was XAE4. During experiment number 5, the concentration of sulfur dioxide in the air was YA. Concentration of sulfur dioxide during the equilibrium during the experiment number 5. Similarly, the concentration of sulfur dioxide during experiment number 5 in the equilibrium case is XAE5. Similarly, in experiment number 6, concentration of sulfur dioxide in the air was XAE6. In the liquid, it was XAE6. This is in the gas, this is in the liquid. During experiment number 7, concentration of sulfur dioxide in the air was YAE7. In the liquid, it is XAE7. So, this YA show us the concentration of sulfur dioxide. The E show the equilibrium condition, and 7 show the experiment number 7. So, this is the concentration of sulfur dioxide at equilibrium during experiment number 7. This XA show the concentration of sulfur dioxide, E show the equilibrium, 7 show the experiment. So this XAE7 show the concentration of sulfur dioxide during the equilibrium in experiment number 7. So during the equilibrium, the concentration of sulfur dioxide in the experiment number 7 was reached to XAE7. So this was a table. Now how can we obtain a graphical relation from this table? How can we obtain a graphical relation from this table? So we can obtain a graphical relation from the above table. Suppose this is XA, E, and this is YA, E. At the start there was no sulfur dioxide in the vessel, there was no water in the vessel, so this was 0. When we enter the sulfur dioxide into the vessel, we enter water into the vessel, we enter air into the vessel, the sulfur dioxide was absorbed in the water, and the concentration of sulfur dioxide in the air was decreased, and the concentration of sulfur dioxide in the water was increased. So we obtained a point. Suppose this is XAE1, and this is XA, this is YAE1. Similarly, after when we increase the sulfur dioxide, the concentration in the gas phase was increased. Similarly, the concentration in the liquid phase was also increased during equilibrium. Again, we further increase the sulfur dioxide into the vessel. The concentration of sulfur dioxide was when we increase the sulfur dioxide into the vessel, the sulfur dioxide was absorbed in the water. At equilibrium, the concentration of sulfur dioxide in the air was reached to YAE3. This is YAE3. This is YAE2. This is XAE2. This is XAE3. Now again we increase the sulfur dioxide. We enter more sulfur dioxide into the vessel. More sulfur dioxide absorbed in the water. Some of the sulfur dioxide was dissolved, but when we study the concentration when we study the equilibrium concentration of sulfur dioxide in the gas phase, it was obtained to be YaE4. And when we study the equilibrium concentration of sulfur dioxide in the water, the equilibrium concentration of sulfur dioxide in the water was come out to be XaE4. This is 3. Again, experiment number 5, the concentration in the air was YaE5. In the liquid it was XaE5. Experiment number 6, it was YaE6 and XaE6. This is experiment number 6. In experiment number 7, it was reached to YaE7 and XA. This is YaE7 and this is the XaE. So experiment number 7, this is 6, this is experiment number 5, this is experiment number 5, this is 6, this is 7. When we combine the whole point, we obtained a linear graph. It shows that when we increase the concentration of sulfur dioxide in the air, the concentration of sulfur dioxide in the water will be increased. Or it can also say that when we increase the concentration of sulfur dioxide in the vessel, the equilibrium concentration of sulfur dioxide in the liquid water will be increased. So when we increase the concentration of sulfur dioxide in the vessel, the equilibrium concentration of sulfur dioxide in the air and the equilibrium concentration of sulfur dioxide in the vessel will be increased. So, and a linear curve will be obtained. And this linear curve was first proposed by Henry. And Henry type curve is obtained from our experiment and from this whole graph and from our table. So this Henry law shows a linear relationship between the concentration of sulfur dioxide in the air and the concentration of sulfur dioxide in the liquid. So the Henry law this graph shows a linear relationship between the concentration of sulfur dioxide in the air and the concentration of sulfur dioxide in the water. So Henry law relation, Henry type relation was obtained from our table and graphs. And what is the Henry law relation between what is the Henry law? The Henry law says that if we increase the concentration of gas above the liquid, then the concentration of the gas in the liquid will be increased. So if we increase, it says, what is the Henry law? It says that the concentration of gas above the liquid is directly proportional to the concentration of gas in the liquid. If we increase the concentration of gas above the liquid, the gas, more and more gas will be absorbed in the liquid. If we increase more and more gas above the liquid, more and more gas will be absorbed in the liquid. So if we increase the concentration of gas above the liquid, more and more gas will be absorbed in the liquid. So the concentration of a component in the gas phase will be directly proportional to the concentration of gas in the liquid phase. So Y is directly proportional to the X. This is the concentration of component A in the gas phase. This is the concentration of component A in the liquid phase. And this is the Henry law. So Y is equal to Kx. Proportionality, when we remove a proportionality, we will put some equal and constant. and this constant is called the Henry constant, and this is the X. So at equilibrium, the relation between YA and XA will be equal to XAE, YAE is equal to F. So again, this is the Henry type relation, Henry law type relation between the concentration of component A in the gas and the concentration of component A in the liquid. So in the coming lecture we will discuss about the interface mass transfer. We will discuss the various topics related to the interface mass transfer. We will discuss the Raoult's law and the other law related to the interface mass transfer. So if you are new to the channel, please like and subscribe. Thank you.